Good morning. This lesson is for my Honors Integrated 1 class, but before I get started, I want to say I hope that everyone is doing all right out there. This is lesson 14.3 or 4, I don't remember. I'll title it correctly on the video. But let's talk about our goals here today. We have 3 goals today. Our first goal is going to be to define exponents and use them to write simplified tables. Our second goal is going to be to create equations that represent the tables with repeating numbers. And our third goal, is to create 2 exponent rules. All right, so let's go ahead and jump into our first goal, which is to define exponents and use them to rewrite simplified tables. By the way, this is all for geometric sequences or geometric patterns, because as we'll see here, exponents are a way to represent repeated multiplication, and geometric patterns are patterns based on repeated multiplication. So we can actually write this in a nicer way. So here I have an example of 5 times 5 times 5, and I can rewrite that with an exponent saying 5 to the 3rd power. And so let me write that translation down just so you know. Translated, this is saying 5 to the 3rd power, which means I'm multiplying 5 by itself 3 times. This is 2 to the 4th power, and that means that I'm multiplying 2 to itself 4 times. So this will actually be 2 times 2 times 2 times 2. All right, so we don't multiply 2 times 4 and get 8. We multiply 2 times itself 4 times. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So please be aware of that. All right, so that's what is meant by an exponent. So now we're going to rewrite a table using exponents. And before we do that, we have to see if we have a geometric pattern. So again, I'm going to compare the next y value by the previous. And so this ratio, to go from here to here, is 6 over 2, and that gives me a ratio of 3. The next ratio, I'm going to take 18 and divide it by 6. And again, that's 3. And I will see how 54 and 18 compare. And again, that simplifies to 3. So 3 is my common ratio on this table, so I have a geometric pattern. So let's rewrite our table the way we did the last time. Remember, the first row stays exactly the same. My x values stay exactly the same. All right, so let's see here. So to go from 2 to 6, I have to multiply by 1, 3, right? So this becomes 2 times 3. To go from 2 to 18, I need to multiply by 3 2 times. So this becomes 2 times 3 times 3. And to go from 2 to 54, I have to multiply by 3 times. So this becomes 2 times 3 times 3 times 3. So now that I have repeated multiplication, I'm going to rewrite it with an exponent. So let me rewrite this with an exponent here. So I have 0, 2, 1, and I'm multiplying by 1, 3. So I can just say 2 times 3 to the 1st power. That's fine. And then this one would be, my row 2 would be 2 times 3 to the 2nd power, because I'm multiplying it by itself twice. And then the last one would be row 3 would be 2 times 3 to the third power, because 3 is multiplying by itself 3 times. So this would be how I would accomplish my first goal, defining exponents and using them to write simplified tables. Hopefully you recognize something that we had in arithmetic tables that were good. We wanted repeating numbers, and guess what we have? We have repeating numbers. And when we have repeating numbers in a table that were arithmetic, we were able to just generalize that and make an equation. For geometric patterns, it's not going to be any different. We actually have enough information now to write an equation. So I'm going to go ahead and erase the board and write what I need next to accomplish the next goal. So I'll be back. I'm back. All right, so let's move on to our second goal. And let me check off the first goal, actually. And our second goal is to create equations that represent tables with repeating numbers. Remember, when numbers are repeating, we can replace it with an x and we have an equation. So I wrote down the original table, and then I wrote down the table with the repeating, or with the exponents. And again, notice my exponent repeats with the row value, my exponent repeats with the row value, my exponent repeats with the row value. We want repeating values, because when we have repeating values, and I need to write this down, you can write the equation. So I can jump from row 3, ... to row x, which means that my y value at row x is going to follow the previous pattern, and it's going to be 2 times 3 to the x power. And all that I have to do to create my equation is say that f of x is equal to 2 times 3 to the x power. So hopefully I've created an equation that represents this table. And again, I'm hoping this is very familiar to you guys, because it's really what we did first semester, and I'm hoping that you're seeing the similarities. And also, the equation should create the table. If I was to plug in 2, I should get 18, because this equation represents this table. I had my repeating numbers, and then when I have my repeating numbers, I can replace the repeating numbers with an x, and I get my equation. So let's see if this equation is any good. All right, so if I plug in a 2, I have f of 2 is equal to 2 times 3 to the second power. But we just saw that exponents are a way to write multiplication in a shorter way. So this actually becomes 2 times 3 times 3. I'm multiplying 3 by itself twice. So 2 times 3 is going to give me 6. 6 times 3, that's going to give me the 18. So I have a good equation. And again, I want to stress this a third time. We can write an equation when numbers repeat. All right? And once we have the repeating numbers, we replace that with an x, set that equal to f of x, and we have our equation. Okay? When you have repeating numbers, you can write the equation. I want to go back to an arithmetic example, and I want to talk about how to make repeating numbers. This table will not have repeating numbers, but I think that this is a really good review to see, because we're going to see how similar, in fact, this new lesson is. We're not learning anything new, we're just applying what we already know how to do to a different operation. So, to go from 7 to 13, I have to add 6. To go from 13 to 19, again, I have to add 6. And to go from 19 to 25, I have to add 6. So I'm going to create my new table. The x values stay the same. The first row stays the same. And I'm just going to write out what we have. So to go from 7 to 13, I have to add 1 6. So this becomes 7 plus 6 times 1. And to go from 7 to 19, I have to add 2 6s. So this becomes 7 plus 6 times 2. And to go from 7 to 25, I have to add 3 sixes, so this becomes 7 plus 6 times 3. Now, this is not going to be a good equation because my numbers are not repeating. But remember, we had a clever way to make this happen, and what we would do is we would still write the same value. Like here I had a 1, here I had a 2, here I had a 3, but I would create the value 1 using the number 3. So instead of saying 6 times 1, I would actually say parentheses 3 minus 2. I have my repeating number, but I still have a value of 1. Again, I need a value of 2. I need to use the number 4. So instead of saying 2, I'm going to put a parenthesis and say 4 minus 2. This has a value of 2, but it also has a repeating number. And I would also do that here with a 5. And I would say 5 minus 2. I still have a value of 3, but I've used my repeating number. So now that we have repeating numbers, we can extend this table to the xth row and get to a point where we can write our equation. So, or get to a point where we can write it for the x row, and from there set that equal to f of x and write our equation. So it becomes 7 plus 6, parentheses, my repeating numbers get replaced with an x, and then everybody inside the parentheses I subtracted 2, and that's how we would write on our equation when we have numbers that don't repeat. Remember we had to do that little trick, so we're going to do that now to geometric patterns. So first, let's find the common ratio. So it's 12 over 24. That reduces to 1/2. This is 6 over 12. Again, that reduces to 1/2. And then this is 3 over 6. And again, that's going to reduce to 1/2. So I have a geometric pattern because I have the same ratio going from each row. All right, and let's rewrite our table here. And I hope that I'm still on the whiteboard. Let me come over here and check before I write a bunch of things that are not on there. Oh, it's going to be close. Now, I'll write it underneath. Okay. I'll write it underneath. So again, my x values stay the same. My first row stays the same. And to go from 24 to 12, I have to multiply by 1/2 once. So this becomes 24 times 1/2, right? Once. And to go from 24 to 6, I have to multiply by 1/2 twice. So this is going to be 24 times 1/2 to the second power. And to go from 24 to 3, I have to multiply by 1/2 3 times. So this becomes 24 parentheses 1/2. Let me learn how to write the number. 1/2 to the power 3. Notice these numbers are not matching like they did over here. But we can do what we did with our arithmetic sequences or patterns, and we can get creative with how we write them so we still have these same values, but we now incorporate the repeating numbers. And once we incorporate the repeating numbers, we have gotten to a point where we can write the equation. So I want the value 1, but I need to use the number 3. So I'm not going to say 1. I'm going to say 3 minus 2. I need the value 2, but I have to use the value 4. So I'm going to say 4 minus 2. I need the value 3. I have to use the number 5. And so here I'm going to say 5 minus 2. And if I was to extend this down all the way to the x row, and I'm so sorry that I'm running out of room, so I'll write it nice and high up here. But if I was to extend this all the way to the x row, dot, 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 I replace my x, everything stays the same, 24 and a half, and my repeating numbers now get replaced with an x, and then it's always minus 2. So the x row would be 24 with a parentheses of 1/2, and then here would be x minus 2. Okay? So, for example, my equation would now be f of x equals 24 parentheses 1/2 x minus 2. And I need to make sure that I'm still on the screen here. I know I'm getting real close to being off the camera here. Oh, and I'm just barely on. Okay. Now, if I was to plug in a 3, I should get a 12. So if I plug in a 3, I get 24 and a half, and then 3 minus 2. Well, 3 minus 2 is 1. So I get 24 times a half to the first power. That means I just multiply by 1/2. And if 24 times a half once, that's going to give me a 12. So this means I have a good equation because when I plug in a 3, I got a 12. And so we get to have repeating numbers doing the same thing we did with arithmetic powered patterns to get the same number. It's the same idea. This is why I wanted to teach it this way in the first semester. And when I had some of you guys trying to make shortcuts and get around doing the tables the way I wanted you to do it, you were missing out on learning how to do this and get comfortable with this, because I knew that in the second semester that this was going to be something that we could actually breathe through this lesson very quickly. So I'm going to go ahead and check off the second goal. I need to erase everything and set up the board for the last goal. So I'll be back. I'm back again. Second time I'm back. All right, we're moving on to our third goal here, and that's to create exponent rules. 2 exponent rules. All right, so what I'm doing is I'm going to use the last example. We already know that this table created this equation that works. We're at that point. But what I did with this table is I added a new row. I didn't put values in here, and I'm hoping we can figure out what value for x goes here and what value for f of x goes here. If I'm going in this direction, it gets smaller by 1/2. So if I go in this direction, it doubles. So hopefully you guys understand why I can put 1 and 48. Right? The pattern continues this way and also works that way. All right. So I want to plug in 2 values. And when I plug in these 2 values, it's going to force you to consider what the exponent is doing to the number. All right, so let's start off. Let me write that out. When I plug in 2 values, it's going to force you to understand what the exponent is doing to a value. Very important. So the first value I'd like to plug in is I'd like to plug in 2. We know that we have a good equation, so if I plug in 2, I should get 24. So example 1, plug in 2, and we should get 24. Right? We already know we have a good equation. So let's plug in 2 to this. And so we have f of 2 is equal to 24, parentheses, 1/2. And now my x is a 2 again, and that's 2 minus 2. Well, let's deal with the exponent first. I now have 24, parentheses, 1/2, and my exponent is 0. We know that these numbers are multiplying together. We also know that when we plug in a 2, we should get a 24 back. This is supposed to equal to 24. Think about what that must mean about this value. What value must this be so when I multiply it by 24, I get 24 back? Let me do example 2. I'm going to plug in a 1, so I should get a 48. Example 1. Example 2. I'm going to plug in a 1, and I should get a 48. So f of 1 is equal to 24, parentheses, 1/2. Now it's 1 minus 2. Because my x becomes a 1. And now I get 24, parentheses, 1/2. 1 minus 2, that's minus 1. We know that we have a good equation. I've already verified it, and I verified it in example 2. But we know for sure that that must be 48 because it follows the pattern. It must be 48 because it follows the pattern. So the question I'm going to ask is, what must a negative exponent do to this value of 1/2 so that when I multiply that to 24, I get 48? What must it do? And you know, I think I'm going to end the lesson here. I'm not going to answer that question, and I hope that you can figure it out. We will discuss it in class. Maybe I'll make another video that explains what it does. But again, I wanted to create 2 exponent rules, so I thought I would create a situation that forces you to tell me what a number to the 0 exponent is, and tell me what happens to a number when I have a negative exponent. Alright, so hopefully we're able to figure that out from this lesson. We will discuss it. So I'm going to go ahead and end it here. Again, I hope everybody's having a good day. I'll see you guys later. Bye-bye.